Well, hello everyone, and welcome to Homework 5. So here we're going to continue the concepts from the prep. So we start out with this first tab, and this is about prices of gasoline. So gas prices are thought to be normally distributed with a mean of $4.50 and a standard deviation of 50 cents. That's 4.5-0.5. If gas prices are normally distributed, then we would expect 68% of gas prices to be within one standard deviation of the mean, 95% to be within two standard deviations of the mean. A national sample of 100 gas prices appears below. Complete the formulas, graph the result, and answer the questions. So you've got here a bunch of cities and the price of a gas in those cities. So you begin, as you did in the prep, by calculating the min, the max, the mean, the median. Those are easy ones, right? The underflow and the overflow, you pull off the graph. So there's your underflow value, there's your overflow value. Then you calculate the range as max minus min, standard deviation. Remember, it's a sample, so that's the .s standard deviation. And then you take the mean, subtract one standard deviation here, subtract two here, add one standard deviation, add two here. Then you use the countif to see, well, okay, how many values appear between minus one and one standard deviation of the mean, and how many values appear within two standard deviations of the mean. Then make your make your graph, and then answer the questions about the graph. When you come over here to the pivot table, this one's a little bit interesting again. Notice that we've got the gas prices. We go 3 to 3.25 and then 3.25 to 3.5. Well, if 3.25 exists on both intervals, then the only thing that could possibly make sense, right, would be that it comes up just short on this interval, and that the 3.25 value is equal on the interval below, and then goes up, coming up just short of 3.5. And we're showing that with interval notation, which is the square bracket, meaning that it includes that value, and then the curve parentheses, meaning that it does not include the upper bound. And as I mentioned before, that's different than the histogram. Histogram does just the opposite, where it shows that it does not include the lower bound, but does include the upper bound. And I'm just mystified why Excel would have designed it that way, but they did. And so then you graph the values off the pivot table using the pivot graph feature. And so that actually should work out pretty well. When we do the formulas, we can we don't have to worry about, like, well, who belongs to who, because we can actually leave a penny in between. So we can go 0 to 3.24 and include both endpoints in the interval, and 3.25 to 3.49 and include both endpoints. So so we can go greater than or equal to, less than or equal to for both endpoints. And then we only have the one down here that's problematic, where we eliminate the upper bound in order to calculate the last one, because it goes to infinity. And then you'll graph that, and you should be all set. So kind of cool. Right, again, why would you want to know this? Well, if gas prices are normally distributed. Oh, and I see that we've got the title from the old one here. Looks like we fixed it there before I distribute it to you. I'll fix this one as well. So fear not, that will be what it should be. Anyway, the reason you'd want to know this is because if you are setting your gas prices, or your government agency monitoring gas prices, you really want to see what variability, if any, there is in gas prices in a particular area, and how that's going to affect consumers. If you're the one selling gas, it helps you set your gas prices.